Hello everybody, my apologies for a delayed video here. Today we are going to talk about simple harmonic motion. This is a ninth video in the series of Physics at Home. Now in this video, simple harmonic motion is what we're going to talk about, and it is a subsection or subset of a bigger family of what is called as a periodic motion. You see a mass here attached to this spring. Periodic motion would mean a motion that repeats periodically. That's periodic motion. In periodic motion, there is what we call a restoring force. That if the object, as you can see here, is in equilibrium position, meaning the weight pulling the block down is equals to the force from the spring. So right now, the total force on this block is 0. And if we pull it down, then the force from the spring is stronger compared to the weight. So what that force is doing is trying to bring it back to the equilibrium position. But by the time it comes to the equilibrium position, it's going to gain some speed, right? So it's going to continue to rise. So when it goes up, now the spring force is smaller than the weight, right? So weight is slowing it down. And eventually it's going to come to a momentary stop. But then once it comes to stop, now weight is more, so it will again bring it back down to its equilibrium position. But by the time it comes there again, it gains speed. So this cycle continues on and on and on. So this is what a restoring force acts as, to bring the position back to its original position, the equilibrium position. If the restoring force is directly proportional to the displacement of the object, then, or the position of the object away from the equilibrium, then that restoring force leads to what we call as a simple harmonic motion. Okay. So in periodic motion, there is a restoring force. In simple harmonic motion, the restoring force is directly proportional to the displacement of the object. So what we are saying is, if you pull by a certain amount, let's say, then there is going to be force from the spring. If you increase that stretching by twice as much amount, the force from the spring will be twice as much. So the position and the force, they are directly proportional, and that is what we call as a Hooke's law of elasticity. Okay, so in the Hooke's law, the force from the spring is equals to how much stretching or compression is in the spring. Okay, so to work this out or understand the Hooke's law first, what we're going to do is attach a car here, because right now the coils of the spring are squeezed and they are holding this together. So to run an experiment, we need to open these coils first a little bit. Okay, with the car, it's going to open it a little more than just a little bit, but that would then we're going to consider as a equilibrium position. Okay, or the position number 1, where there is net force is 0. Okay, so let's see. Alright, so I have put tape on this car, and then I'm going to attach it to the spring. Alright, so I have opened up each coil. It's separated now. Now we are ready to run this experiment. So what I'm going to do at this point in time is I'm going to measure the total length here. Okay, so when I say total length, I'm going to assume, let's say, this wooden, surface here is going to be my 0, and then from here up to the bottom of the spring, how much is the length? So I have my meter stick, it is 0 right here, so I can place it against that surface, and then I'm going to try and read. Keep my eyes leveled so that I can read right there, wherever the bottom of the stick is, bottom of the spring is. So which now is 12.4. oh, no, sorry, 12.8. Yeah, 12.8, 12.7, somewhere around that. So 12.8 centimeter. So I'm going to make that. So my first measurement, 12.8 centimeter. Now I don't know how much is the mass of the spring, but I don't care. What I care is how much the spring gets stretched further if I attach a washer on this. Now this is a 5.5 gram washer. So if I attach it to this car, then it's gonna, pull more down, right? Because now the total weight is higher. So do that. Alright, so the washer is here, attached to the car. So you can see now it has stretched further. And we can make sure that indeed it is the case. So now if I'm eyeballing it, so it's 14.4 or 3, yeah, 14.3. 14.3 centimeter. So the first situation, the mass was 0 grams, because I'm assuming that would be my starting position. And in the second position, I've added 5.5. So with the 5.5, whatever is the difference between the two is how much is it stretched further, correct? So 5.5 grams. And if I continue to add more and more washers, then I'm gonna get the amount with which it gets stretched, yeah, farther and farther. So that will be one part of the experiment where I attach the mass and measure the length. I don't want to run the whole thing here, because in the section after this that you will see all the data. Okay, but in addition to this, okay, what we also want to look at, what we also want to look at is the oscillations that, once you attach the mass, then we saw that it oscillates up and down if you stretch it by a certain distance, right? Now, in doing so, I am gonna attach a steel ball here. Okay. So this steel ball is 67 grams. Yeah. Oops, sorry. The steel ball I'm gonna attach here to the spring. Alright, so now it's going to stretch it by whatever distance. Now I don't want to worry. I don't need the distance here. What I want is the time it takes to oscillate, going from bottom to the top and come back to the bottom. So that would be called as one oscillation. I'm going to time it for 10 oscillations. Now you have seen this before in the first video where we were trying to measure the mass of the ball. But in this section here, we are going to introduce how the simple harmonic motion and the mass and the spring constant, they are related. Okay. Let's see. All right. So time to start here. So this is 67 grams. So let me make that. So now simple harmonic motion. So first mass is 67 grams. And I'm going to time it for 10 oscillations. So 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh boy. Forgot to start. This did happens. Let's do it one more time, because I need to do it 3 times anyway. So 1, 2, 3. Oh, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.84. I don't know if you all can see this. 8.84. Alright, so time 1 is 8.84. I'm going to repeat it 2 more times. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.87. And let's do one last time. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 8.87. So we have 3 times. Now if I attach the mass, so now the new mass is 67 plus 5.5, so 72.5. So 72.5. Let me do it again 3 more times. Sorry, 3 times. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.19. Reset. 1, 2, 3, go. 1, 2, 9.24. 1, 2, 3, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.2. And I'm gonna repeat this, 3 more times by adding, 1 washer each time. So it will be, steel ball was the first reading, steel ball plus washer, the second reading, steel balls plus 2 washers, then 3 washers, and then 4 washers. So total 5 readings I'm gonna get. And then I'm gonna measure the time for, 10 oscillations. And in the next section, we're gonna see a small analysis of what's going on. And after that, we will see a video on how we're gonna use to plot for the Hooke's law and also for simple harmonic motion, and gonna see how the spring constant from the Hooke's law and the simple harmonic motion, how close they are with each other. Here we see the situation for the Hooke's law, where we attached one car and it stretches the spring by a distance x1, let's say. And as the spring is stretched, then the force from the spring F1 is pointing in the opposite direction, right? So spring is stretched downward, force is upward. And that leads us to the equation for the Hooke's law as, so force from the spring equals to negative K times X, where K is spring constant and X is the length which it gets stretched or compressed, the spring. Okay, so here we're going to make a slight adjustment and call this as delta X. So delta X is the amount of stretching in our case. And this stretching here, we are going to attribute to this item here, delta X. This was an additional stretching caused by adding a washer to the car, right? Car plus 1 washer. That's how it was. And that led to the force from the spring as F2, which was causing the X2 extension, right? And the difference between the X2 and X1 was, the delta X, as we see here. So this delta X was because of that extra washer attached. Now the reason we're gonna think about it in this fashion is because sometimes to open the spring it needs a little bit of minimum weight, as we discussed in the video earlier. Now the negative sign is just a responsible or indicating that if the spring is stretched, then it wants to get compressed, right? By it. So the force is in the opposite direction of whatever is happening to the spring. So if we think about only the magnitude, we can get rid of that negative sign. So let me rewrite this here. So force from the spring is K and delta X. So then if you plot this, force from the spring in Newton and delta X here on the y-axis, then this turns out to be a straight line, okay, and with an equation as y equals to mx plus b. Now this is gonna almost pass through the origin, so the b is almost 0. Okay, so we left with equation y equals to mx. And if we correlate this y equals to mx with the Hooke's law equation, then on the y-axis is the spring, correct? Force from the spring. On the x-axis is the delta x, correct? Then m, which we know is the slope of the line, right, will be represented by the spring constant. Okay, so the slope here represents the spring constant k, and which is y over x, right? So the unit is Newton per meter. And if we continue adding the washer, we're gonna get all kinds of points everywhere. And then using a curve fit, linear curve fit, we would get that line and that equation. Okay, so this would take care of the Hooke's law. This was the part 1 of the experiment. Part 2 of the experiment is the simple harmonic motion. Let me get rid of the washer here and write it here, car plus 1 washer. So the simple harmonic motion, here we see the same, let's say, object. And then that object, actually that was a steel ball here, but I believe we get the idea. And at this dotted line here represents the equilibrium. Okay, so this is the equilibrium position where the weight of the object is equals to the force from the spring. And if you stretch the spring by a certain amount, yeah, then we can see the imbalance between the forces. The weight is smaller compared to the force from the spring. So since there is more pull upwards, the difference between the force from the spring and the weight is now the restoring force, which tries to bring the block back to its equilibrium position. But as it rises, it gains speed and continues to rise up until it goes to the other opposite side, right? So at this position, you can see now the force from the spring is now smaller than the weight. Again, there is imbalance between the forces. So the difference now between these two is now acting the restoring force, trying to bring the block back to its equilibrium position. But in doing so, again, it continues to move past the equilibrium and we go back to the earlier initial position. And the time it takes to go from here to up and then back, okay, this is what we call period. And this period, t, is equals to 2 pi under square root m over k. This is, from the simple harmonic motion. And m is the mass, and k is spring constant. Now if we square both sides, then we're going to end up with t squared equals to 4 pi squared times m over k. Now let's say we plot t squared on the y-axis and mass on the x-axis. So this is kilograms and this is second squared, right? This also comes out as a linear equation. Again, y equals to mx plus b. One more time, b is gonna be almost 0, so it's y equals to mx. Now think about this here, y equals to mx. Y is represented, y represents t squared, correct? X represents mass. And if we look at the equation here, t squared and m are taken. What is remaining? 4 pi squared divided by k. So the m, which is the slope, represents 4 pi squared divided by k. So we can get, k here. I'm going to call it as k1 because this is in the part 1 of the experiment and this is the part 2 of the experiment. So this k here I'm going to call as k2. And we can always, then calculate the percent error between the two, which would be, use this space here. So it will be the absolute value of the difference between the two. Since both of these are experimental, then, we don't know what is the actual spring constant supposed to be. So there is no theoretical value. Hence, we're going to take an average of the two and divide it with that absolute difference on the top, multiplied by 100. In the next section, I'm going to quickly show you how I've used the Excel sheet or Excel plot to plot, both the Hooke's law and the simple harmonic motion, and how the spring constants get pretty close to each other. Alright, so here we see the two plots. The top one is for the Hooke's law and the bottom one is the simple harmonic motion. For the Hooke's law, this column here represents the lengths of the spring that we measured. The first one was just with the car, then the second one was car plus 1 washer, then 2, 3 and 4. Okay. Then the difference, so we said that the initial position was the 0, so second one would be whatever the second number minus the first gives us this number. Okay, and then whatever the third value minus the earlier or the first one gives us this one. Okay, and so these are the lengths of the spring. So just with the car we called it 0. With 1 washer it got stretched by whatever amount, and 2 washers, 3, 4, so on and so forth. These are all centimeter, so divide by 100 gives us in meters, which are right here. Then the objects attached were car and then washers subsequently added. The difference between the difference of the masses was, first it was just the car, then just 1 washer added, then 2, 3, 4, and each washer is 5.5 grams. And then divide by 1,000 gives us the change in the mass, right? Delta M. So the mass attached to the spring is going to have weight, and the weight attached to the spring is equals to the force of the spring, as we saw earlier in the video. So this mass here times 9.8 gives us the force from the spring. So earlier we called it 0, and then with each subsequent washer, the force from the spring increased, right? So force from the spring is directly proportional to the displacement, which, if we take these two columns and then go here, insert and scatter, so we get this plot, right? This plot is similar to this plot, looks the same. We just added labels, okay? What we also added was a trend line, a curve fit, a linear curve fit. The way you do that is, while the chart is selected, you go to the top here and then under the design, add chart element, trend line, more trend line options, and then we can see it here. We can select whichever trend line we want. So since it looks linear, so I've chosen linear. What we also want is the equation of this line. So, which if you go at the bottom, then it says display equation on chart. So you can see right there, that's the equation. And you can see it's the same equation right here, just different format. Right? So I increased the font size so it's readable. And then, the X and Y labels, chart element, axis titles, and then you can select these and then, type whatever is your label. So I'm gonna delete this plot from here because I already have that plot. Yeah. So as we discussed, the slope of Hooke's law plot is the spring constant. So K1 is that slope. The second plot, the simple harmonic motion. Earlier, first trial was just the spring steel ball. This was 67 grams. Then we added one washer, which is additional 5.5 gram, and then 2, 3, 4. Yeah. Then divide by 1,000 gives us mass is attached as in kilograms. Yeah. Then these three are the times for the 10 oscillations. Average of these is here, divided by 10 gives us the time for one oscillation, which is we call it period. Square it and gives us that number. Repeat for the next masses. So we have the mass and t square. Yeah. And again go to insert, chart, do this. And you can see this is my t square on y-axis divided over m on the x-axis plot. And this plot is the same as here, except it looks a bit different because this plot here, we see 0 to maximum of the mass and 0 to maximum of the t square. What I did was I shrink the view to only where the plot is. As you can see it right here at the bottom left corner is no longer 0, 0. Origin is farther away. But then I again the curve fit, you can see is again the same way we did it earlier. It's a linear fit. I added the equation, added the titles, and the slope here represents 4 pi square divided by k. So to calculate k, we have to switch k and slope. So k becomes 4 pi square divided by, k becomes 4 pi square divided by slope. That turns out to be the K2 value right here. As you can see, that's the equation. Yeah, I got it. And these two are my spring constants. They're, close enough, I believe. And then percent error is about 7.5%. Okay. So, as you can see, Hooke's law and simple harmonic motion, both of these concepts, are giving us the same exact spring constant. Okay, not same exact, but pretty close spring constant. All right. So I hope you enjoyed this video, and next video will be the last video in the series of physics at home. That would be about buoyancy. Have a good one.